Hi class, welcome back. Today we're going to be doing conditional probability and the multiplication rule. So let's get started. Okay, so we'll cover these things. Conditional probability is read the probability of A given B. And it means basically the probability of A given that B has happened or that we know B. And basically it's a probability of A given B is equal to the probability of A and B divided by the probability of B, which is also equal to the number of elements in A and B divided by the number of elements in B if they're equally likely. To understand that, let's draw a Venn diagram. Okay, so say our universe is this, and let's say this is set A, and this is set B. This is the set A and B. Okay, that's both of them happening. So now let's look at the probability of A given B. Given B means that we're in B. We know B has happened. Okay. So what's the probability of A given B? Well, it's the amount of A that's in B. So it's the number of A and B. This part right here, this part of B. So it's the number of elements in A and B divided by the number of elements in B. I can divide top and bottom by the total number in the universe. So I can also write it as the probability of A and B over the probability of B. I hope that helps for your understanding. Okay, so let's do an example. Say we have the following list of lung disease and smokers. This whole thing adds up to 100. And either they're a smoker or not a smoker, they have lung disease or they do not. So let's answer a couple of basic probability questions, and then we'll do a couple of conditional probabilities to get a feel for what's going on. Okay, so probability that he's a smoker, it's basically these two right here. So we can add that up, 0.12 plus 0.19 is equal to 0.31. Okay, probability does not have lung disease. We add up these guys right here, does not have lung disease. So that's equal to 0.19 plus 0.66. So that's equal to 0.85. Okay, lung disease and is a smoker, so that's an intersection of smoker and has lung disease. So it's this one right here. All right, so that one's just read right in the table, 0.12. Now, has lung disease given that he's a smoker. Our reduced sample space, our reduced area is he's a smoker, right? So we're just dealing with the smokers. So that's the denominator. All right. So that's the probability of A. That's just the probability of B. B is that he's a smoker. So that's 0.31 or 31 out of 100. We can look at these as a total number out of 100. And what's on top is that he has lung disease and a smoker. So that's this one. So this part has lung disease out of this whole part here. So it's this part out of this whole part. So it's 0.12, and that's equal to that's equal to 0.387. Okay, has lung disease given that he's not a smoker. Now we're in this reduced. This is our B, right? That's our reduced sample space. So that probability is, given that he's not a smoker, well, we have 0.69 or 69 out of 100 for the denominator. And actually, I'll just write it over here. Probability that he has lung disease, given that he's not a smoker. Okay, that's equal to 0.69. And the top is that he has lung disease and is a smoker. It's 3 out of 69. So I'll write that over here too. And that's equal to 0.043. So much less likely to have lung disease if you're not a smoker than if you do. So the moral of this story is don't smoke. If you're not addicted to it, don't smoke. Okay. So the idea of dependence and independence, two events A and B are independent if the probability of A given B is just equal to the probability of A, meaning that A doesn't care if B's happened at all, right? It's completely independent. And by symmetry, you can write it this way. Okay, so here's some examples. You flip a coin, the first one's heads. The second, independent or dependent? Completely independent. A friend comes to class, you, might be dependent, might be independent. Stock market up today, tomorrow, there could be general trends, so that could be dependent. You roll a die, it comes up 6. Next roll, completely independent. Weather's nice today, what about tomorrow? There's generally nice times and then there's generally stormy times, so it's probably dependent. And you get an A on the next test. On this test, what about the next one? It's probably dependent. You know how to study and everything, so it's probably more likely that you get an A again. Okay. Let's put a solid example here. So promotion and gender. Say we have this data for a company. And the question is promotion and gender dependent on one another? Well, what do you have to do? Okay. Well, you have to see if the probability of promotion, does that equal to the probability of promotion given that you're a male? And if that's a probability of promotion given that you're a female? Well, the probability of promotion is just how many people got promoted? Well, 54 out of a total of 270. And that's equal to 0.2. What about the probability of promotion given that you're a male? That's equal to, well, now we're just in the male area. Just here. That's our reduced universe. Okay. So we have 46 promotions, but there's 230 men in this company, and that's equal to 0.2. What about probability of promotion given that you're a female? Well, now we're in this reduced sample space, or this reduced universe. Now we're just talking about females. There's 40 females, and 8 got promoted. That's equal to 0.2. So we do have this condition that they're all equal, and that's the test, or that's the definition of independence. So it's independent. So we got independence. Okay. All right. Another example. Okay, another example. What is the probability that a man would ask for directions? Okay, that a man. So that's a conditional probability. We're just talking about men. So it's a probability that a man would ask for directions given that you're a male. Right now we're just concerned about the men. So that's equal to, well, this is on the denominator. That's a probability of men. And this is a probability of ask for directions and men. So that's equal to, well, probability of men, if we add up all these, that's 50. It's 50, half men, half women. Okay, probability of ask for directions and male, well, that's the intersection. Here's all the people who ask for directions. So the end situation is right where they intersect. So it's this one, 0.12. And that's equal to 0.24. What proportion of drivers consult a map? Well, you just add up all these, right? So that's 0.25 plus 0.14, which is equal to 0.39. And our gender in asking for directions independent. So we have to say, well, what's the probability of asking for directions? You have to say, what's the probability of asking for directions if you're male? And what's the probability for asking for directions if you're female? The probability of asking for directions, we already is we just add up these two, so that's 0.4. Probability of asking for directions given that you're a male, well, that's equal to the intersection of ask for directions is equal to 0.12 over 0.5, so that's equal to 0.24. Already it's not equal, so we know it's dependent, but we'll continue. Probability of asking for directions given that you're female, we're just talking about the females. We got 50% for females, and asking for directions is 0.28. So that's equal to 0.56. Since they're not all equal, right, probability of A given B is equal to the probability of A for independence. They're not equal, so we have dependent. Okay. Okay. So we can take our conditional probability and we can multiply both sides by the probability of B and get what probability of A and B is. So basically we multiply both sides by this, so that brings this up here. And so here the probability of A and B is equal to the probability of B times the probability of A given B. And by symmetry, we could easily interchange A and B. So we have probability of A and B is equal to the probability of A times the probability of B given A. That's the general multiplication rule. Let's see an example. An assembler supplied 10 electronic parts, of which 3 are defective. If 2 components are selected at random, what's the probability that neither component is defective? Neither component is defective. Okay. So we have probability that we have not defective on the first and not defective on the second. So that's equal to the probability of not defective on the first times the probability of not defective on the second, given that we selected one that was not defective on the first. Well, not defective out of first is, well, there's 3 defective, there's 10 of them, so it's 7 out of 10. Now here's the part. Since we took one out, how many are left? There's 9 left in there. How many of those are defective? 2, so 3 are still defective because we took one that's not defective. So there's still 6 that are not defective out of 9. Okay. And that's equal to 42 over 90. which is equal to 0.467. So there's an example of that one. Okay. Now, if A and B are independent, then the probability of B given A is just equal to the probability of B. So this just becomes the probability of A and B is equal to the probability of A times the probability of B. We can just multiply them. All right. So if the probability of having a boy is 51%, and you plan to have 3 kids, what's the probability that you have 3 girls? Okay. Okay, well, probability of 3 girls, right? Probability of a girl and a girl and a girl is just equal to the probability of a girl times the probability of a girl times the probability of a girl, which is equal to just the probability of a girl cubed. Now the complement rule gives us the probability of a girl is a complement of 0.51, so it's 0.49. Now if we cube that, we get we get 118. Okay, so if they're independent, you can just multiply them. And that's the idea there. Okay. Say we have political affiliation, this data here. If we pick 3 people at random, what's the probability that all 3 are Democratic? Okay, well, there's a total of 122 out of 237. So officially, by the general multiplication rule, we'll have the probability of this event is equal to, well, there's 122 Democrats out of 237. And then we'd have to multiply 121 out of 236 after we selected 1, and then 120 out of 235. That's basically if we picked them without replacement. That's equal to 0.135. Well, I hope this video was helpful and that you enjoyed your learning. Cheers.